20 Hz is the frequency where a sound wave stops being just noise and physically trembles the human body. Powerful bass lines turn a small room into a full-blown concert hall using a single vibration. A tiny component is responsible for this intensity, but this is just the beginning. How does a static box achieve such dynamic control over the air? To the eye, the exterior looks motionless, but beneath the shell operates a machine where engineering merges with music to transform silence into a sonic explosion in seconds. At first glance, it seems like a simple device, but in reality, it controls the atmosphere itself using metal sheets. One can notice how copper coils, thinner than a strand of hair, are wound to convert electricity into emotion. Absolute precision drives the assembly. It gets more complex further on. The sound created touches the deepest corners of feeling. $11 billion is the sum the global smart speaker market generates in just 1 year. Behind this figure, technology giants invest hundreds of millions of dollars annually to refine the listening experience, chasing deeper bass. But this is just the beginning. Enormous factories operate around the clock. Why produce such volumes daily? It seems like an endless stream of devices, but more than 150,000 units are needed every single day to fill an entire city with sound in just 24 hours. At first glance, the device appears simple, but in reality, it does not create sound the way we imagine. Every melody, every rhythm, and every surge of bass is nothing more than air in motion at a microscopic scale. One can notice how invisible vibrations permeate the room. Engineers design this precision to evoke emotion and connection. Thus, energy fills the spaces where we live and work. 1,000 degrees Fahrenheit is the minimum threshold required to forge the silent engine of every sound system. Behind the precise audio emitted from a modern speaker lies the magnet, an essential component often hidden from view. Two distinct types dominate this high-tech industry. Ferrite is known for being heavy, affordable, and durable, while neodymium is prized for its lightweight nature and exceptional strength despite a higher cost. Why is the specific material chosen so carefully for each unit? Engineers weigh the options based on the desired audio performance. The answer lies in the specific size of the driver the magnet must power. The creation process begins within the blazing heat of industrial furnaces. But this is just the beginning of the transformation. A precise mixture of minerals and rare earth metals melts into a uniform liquid after several hours of intense processing. One can notice how the molten material is poured into precision molds and compressed to form magnetic blanks. Typically, these take cylindrical or ring shapes, depending strictly on the specific speaker design. At first glance, the cooled metal block appears inert, but in reality, its internal structure is about to change forever. Inside shielded chambers designed to prevent external interference, high-power systems discharge immense electrical pulses. This surge is powerful enough to pull steel tools off a nearby workbench. It is visible how the energy forces the internal magnetic domains to align perfectly, creating a permanent magnet with strong, stable fields. The high temperatures used earlier now help stabilize this new structure, ensuring durability and resistance to demagnetization. And this is not the limit of the engineering precision involved. Once cooled, each blank moves to precision machining stations to be milled into its final exact dimensions. The component is now ready for assembly into the speaker chassis. Thousands of electrical signals convert into precise mechanical motion as the copper voice coil enters the vibration mechanism beneath the freshly completed magnet assembly. This component behaves exactly like a miniature motor throughout the operation. Why does copper remain the almost irreplaceable choice in audio engineering? It might seem that modern synthetic alloys could offer lighter or cheaper alternatives for the coil, but pure copper provides the necessary conductive stability, coated here with an ultra-thin layer of insulation. One can notice how this protective coating ensures optimal conductivity without the risk of short-circuiting between the strands. But this is just the beginning. High-precision automatic winding machines wrap the wire into a cylindrical coil around a central core or bobbin. It is visible how the system controls tension, speed, and direction with absolute rigidity during the rotation. Each individual turn sits in the exact position required to generate a stable and uniform electromagnetic field. At first glance, winding looks like a simple mechanical process, but in reality, it is programmed to match the intended design with micrometer precision. Depending on the loudspeaker type, the coil consists of a single layer or multiple layers stacked together, formed like a sophisticated muscle bundle at the heart of the moving system. The process is only gaining momentum. Consequently, the entire coil is coated with heat-resistant adhesive to secure and protect it during operation. Thus, electrical energy transforms into motion, the true soul of sound. Zero mechanical distortion is the primary goal when selecting materials for high-end loudspeaker components. If the voice coil acts as the engine generating motion, the diaphragm serves as the amplifying arm that transforms this kinetic energy into audible sound. Why do engineers select materials as varied as titanium or carbon fiber for this task? The acoustic signature depends entirely on physical properties. These specific materials are chosen to enhance responsiveness without introducing distortion. Standard production typically utilizes resilient substances like polypropylene, fiberglass, pressed paper, or mylar. Sheets of these materials are cut into circular blanks, but this is just the beginning of the transformation. Inside the thermal press, metal molds with fixed geometry descend to compress the material at high temperatures. It is visible how the flat blanks take on the characteristic cone or dome profile under the immense force. Pressure, temperature, and pressing duration are precisely tuned to prevent warping or edge tearing during formation. Because even a single millimeter influences the final acoustic performance, geometry is critical. It seems simple to shape a cone, but in reality, details such as rib patterns, depth, and cone angle are carefully engineered to ensure proper frequency response. Some diaphragms undergo additional surface treatment to increase durability. One can notice the application of protective coatings that guard against moisture and static charge. It gets more complex further on. Therefore, technicians verify uniformity using advanced laser scanning systems. One can observe the equipment mapping the surface to compare every contour against the original design blueprint. Through this balance of optimized materials and tightly controlled geometry, the components achieve near-perfect consistency. The diaphragm leaves the factory ready for the next stage of assembly. 0.1 millimeters is the absolute maximum error margin allowed during the magnetic assembly integration phase. This stage determines the precision of the entire driver operation. Why must the separate components, including the magnet, pole ring, and top plate, align with such extreme rigor? At first glance, stacking these heavy components seems like a straightforward mechanical task. But without this perfect geometric unity, the correct magnetic gap for the voice coil would simply not exist, rendering the driver useless. Therefore, technicians build a unified magnetic module where every part locks into position with absolute accuracy. The magnet takes its place first, followed immediately by the pole ring and top plate, which are pressed firmly into position by a specialized alignment machine. One can notice how sensors embedded deep within the system continuously monitor for even the slightest deviations. They adjust the mechanism automatically to maintain those tight tolerances. When the magnetic components have been positioned correctly, the technician installs the mechanical centering collar to secure the axis of motion. This prevents the magnetic assembly from rotating or shifting during high-volume operation. It gets more complex further on. At this point, the adhesive application stage becomes especially critical. An automated dispenser applies glue in a closed circular pattern around the bonding surfaces. It looks outwardly simple to dispense glue, but in reality, pump pressure, flow rate, and volume are all algorithmically controlled. This precise calibration allows the adhesive to spread evenly into the guide grooves without foaming, without overflow, and most importantly, without disturbing the concentricity of the magnetic assembly. Only a few seconds later, the adhesive begins to cure. This creates an initial bond that locks the module into a single solid structure. Finally, the spider is bonded onto the frame, ensuring the voice coil moves strictly along one axis without lateral drift or twisting under high-frequency oscillation. Once the spider adhesive has fully set, the magnetic mechanical assembly is unified, completing a fully formed driver core. When the magnetic assembly is perfectly aligned, the speaker frame receives its two core components, the voice coil and the diaphragm. The equipment gradually positions these elements, as the coil acts as the source of motion, and the diaphragm becomes the surface that delivers sound. These two elements cannot function effectively without each other. The process begins with the coil being placed into the narrow magnetic gap between the magnet and pole core. Here, a deviation of only fractions of a millimeter can alter frequency response and sensitivity. Depending on the speaker design, the coil is mounted either by hand or by automated pick-and-place systems, after which its leads are soldered to electrical terminals for connection. And this is not the limit. At the same time, the diaphragm, made from compressed paper, polymers, or carbon fiber materials, is positioned and bonded directly to the coil using specialized adhesive. This stage requires both mechanical precision and skilled craftsmanship, because even slight misalignment can cause coil rub and distortion. It is here that a speaker's clarity and accuracy are truly shaped. Once the voice coil and diaphragm have been securely bonded, the assembly is immediately placed into a specialized curing chamber for anywhere from 20 minutes to several hours. This stage allows the heat-resistant adhesive to fully harden, locking every component in place and forming a stable mechanical structure while still preserving the diaphragm's natural flexibility for sound reproduction. Next, technicians perform a manual inspection using directed light to examine every bonding point. It is visible how the beam highlights the joints to ensure the diaphragm and coil are fixed exactly as designed. The unit leaves the station perfectly free of misalignment and with no contact against the magnet. Two favored materials, medium-density fiberboard and birch plywood, act as the critical starting point for the loudspeaker's structural stability. The production line transitions from component fabrication to cabinet construction, a stage that fundamentally determines the overall acoustic performance. Why are these specific dense materials chosen for the enclosure? The wood panels arrive at the processing station in raw sheets. They provide the necessary structural stability, excellent acoustic properties, and cost efficiency required for high-fidelity sound. Automated computer numerical control machinery cuts the wood panels to exact dimensions. Every cut must match the original blueprint with minimal tolerance to ensure a perfect fit. A deviation of even a few millimeters can create air leakage, which would weaken the bass response and reduce system stability. Therefore, the blades move with absolute precision to shape the raw material. But this is just the beginning. One can notice how the shaped panels move to the assembly station. At first glance, joining wooden panels seems like a simple carpentry task, but in reality, it requires a dual approach using industrial adhesives and mechanical fasteners. The adhesive chemically bonds the surfaces, while screws reinforce structural rigidity. This ensures the cabinet can withstand continuous vibration at high playback levels without rattling. Inside the enclosure, technicians strategically place structural braces at high resonance points. They accompany these braces with damping materials such as thick acoustic foam or mineral wool. These elements reduce internal standing waves and suppress unwanted resonance, resulting in a cleaner and more controlled output. Simultaneously, precision tools, machine openings for the woofer, tweeter, bass reflex port, and signal terminals. It gets more complex further on. Each position is calculated according to crossover frequency and internal volume. This strict arrangement allows every driver to perform at full potential without interfering with the others. Once the wooden body is structurally complete, its exterior is finished with vinyl wrap, lacquer, or acoustic fabric. It is visible how this layer protects the enclosure from moisture and warping, while subtly shaping surface reflection characteristics during playback. The loudspeaker cabinet becomes a true audio instrument only when it enters the final assembly stage. Here, each acoustic element is installed by hand, following a carefully structured sequence. Technicians begin by lining the internal walls with additional damping material. This reduces internal resonance so that sound can emerge cleaner, clearer, and free from muddy low-end buildup. Transition to the next level. Signal wires are routed through narrow internal channels and connected to the crossover board. Cable positioning is just as critical as the components themselves, because it must avoid electromagnetic interference. Furthermore, the wiring must never obstruct airflow within the enclosure. Afterward, the drivers, woofers, and tweeters are seated into their designated mounts. One can observe how technicians tighten every screw to a calibrated torque. Too much force risks deforming the frame, while too little can cause vibration or mechanical noise during playback. Once the wiring and crossover network are fully connected, the cabinet undergoes a structural inspection. Panel air tightness, port alignment, and mechanical rigidity are verified one by one. And this is not the limit. The loudspeaker moves into the critical testing phase. Each unit is scanned for mechanical resonance using vibration sensors to detect flaws. Selected samples are placed inside an anechoic chamber for full frequency response measurement from 20 Hz to 20 kHz. The system compares the result to a reference curve and rejects anything outside tolerance. Some models are driven at high volume for hours to simulate real-world stress, ensuring durability. Only after passing all stages is the speaker cleaned and prepared for packaging. It is placed into a shaped cradle and cushioned with shock-absorbing foam. The product, once merely wood panels, is now ready to play its first notes. Thousands of individual components are integrated into a single system during the final testing phase. Every part plays a critical role in the overall architecture. Why is uncompromising quality control maintained until the very end? The device appears ready for use. This ensures that the acoustic structure delivers emotion in its purest form to the listener. At first glance, it is merely a device for producing sound, but in reality, it is the result of absolute precision engineering. One can notice how the casing remains rigid while the internal mechanisms function, and this is not the limit. Thus, the complex assembly reaches its conclusion.